In this video, we will be doing a little refresher on grade 10 linear systems, while also moving forward to the grade 12 extension. So in grade 10, we looked at the intersection of two lines, and there were three different arrangements. And those arrangements were, we have two lines that actually intersect at a single point. We had two lines that were parallel and distinct and had 0 points of intersection, or we had two lines that were one on top of the other. And in that case, we had an infinite number of points of intersection. Now, if we were to graph two lines, we could clearly see how many solutions we have. But we could also solve linear systems using substitution or elimination. And something special happens when we try to solve a system when there are 0 or an infinite number of solutions. So let's see what happens. So this linear system here, 6x minus 4y equals 12 and negative 3x plus 2y equals 5, has 0 solutions. Let's try to solve it and see what happens. Now, if I were to see an equation like this with the x's, y's, and the constants lined up, I personally would do elimination. So that's what I'm going to do. I'm going to multiply this line by 2 to get negative 6x. This one I'm just going to copy paste. So I'm choosing to eliminate the x's. Now, because my x's have opposite signs, I'm going to add. And when I add, 6x plus negative 6x is 0. But then for the y's, negative 4y plus 4y is also 0. So I have 0 on the left side. But then 12 plus 10 is 22, which clearly 0 does not equal 2, so we end up with this false statement. So my variables disappeared altogether, and then I end up with a false statement. That's my clue that there were 0 solutions here. And if I were to take my original equations here and rearrange them, put them both into y equals mx plus b, I would end up with both equations having the same slope, but different y-intercepts. So actually, why not do a little refresher on that? So for the first equation, I'm going to isolate for the negative 4y, bring the 6x over, the 12 was already there, and then I'm going to divide everything by negative 4 and reduce. So I have 3 over 2x minus 3. Then I'll take my other equation, I'll isolate for 2y, so 3x plus 5, divide everything by 2, and I end up with 3 over 2x plus 5 over 2. So we can see we have the same slope, so our lines are parallel, but we have different y-intercepts, so they're distinct lines. So parallel and distinct. I can see that nicely in y equals mx plus b form, or if I tried solving the equations, I would end up with this false statement. Now let's look at a scenario where we have an infinite number of solutions. So again, I'm going to choose to do elimination here. I'm going to multiply this line by 3 to get 12x, and this one by 2 to get 12x. So I end up with 12x plus 24y equals 18, and then 12x plus 24y equals 18. Well, we can already see that the lines are identical, but when I subtract, everything cancels out, and I get this true statement. These lines are the exact same. We call these coincident lines. And because they're the exact same, we have an infinite number of solutions here. And here we can really see that the lines are identical because when we multiplied the lines by a number, they ended up matching. if I were to convert into y equals mx plus b, they would be identical as well, slope and y-intercept. Now, the connection in the other equation was that the x's and the y's had similar coefficients, just opposite signs. But if you looked at the constants, they were completely different numbers. So the coefficients of x and y lead to the slope, whereas the constant leads to the y-intercept. So that was different. So let's conclude it in this little table. How can we determine the number of solutions a linear system will have? For the row that says standard form, we're going to talk about if we're actually going to solve the equation, like with elimination or substitution, what would happen. So if I'm going to have one solution, both of my variables do not disappear. I actually end up with x or y equals a number. But also another important distinction is the coefficients of x and y are not related to each other. If I multiply one of the equations by a value and I match my x's, the y's will not match. When I have zero solutions, I end up with a false statement, like 0 equals a number that it doesn't. And if I have an infinite, I have a true statement, like 0 equals 0. And for these ones, the x and y coefficients will match for both the 0 and the infinite solutions. But for the 0 solutions, the constants will not, whereas for the infinite, every single part of the equation will match. For y equals mx plus b, if I have one solution, we will have different slopes. If I have 0 solutions, we'll have the same slope, but a different y-intercept. And for infinite, they're the exact same line. Now, we're going to add on a little bit of terminology for linear systems, something we didn't use in grade 10, but we're going to start adding it into grade 12. A consistent system is a system that has one or an infinite number of solutions. So if there is some sort of point of intersection, whether it's one or a lot, it's called a consistent system. An inconsistent system has 0 solutions. So when we have two lines in a two-dimensional area, if they're parallel and distinct, we will have 0 solutions. Coincident lines I've already mentioned. They're identical lines, they have the same slope and intercepts, and they're just lines that lie on top of each other. So let's try out these conclusions that we came up with. We're going to state the number of solutions for each system, and we'll justify our answers. I'm going to say the justification out loud, unless I have some work to show. So for the first system, my equations are both in y equals mx plus b, and I notice that they have the same slope. So the lines are parallel, but they have different y-intercepts, so they're distinct lines. And that means we're going to have 0 solutions. For the next one of my equations is in y equals mx plus b and the other isn't. So I'm just going to convert the second equation into y equals mx plus b as well, and then I'll just compare the slopes and y-intercepts. Okay, and when we divide by -2, we get 3x minus 5. They are identical, so infinite solutions. The next one, they're both in standard form, and I can justify my answer in two different ways. If I look at the coefficients of x and y here, I don't think there's really a connection. So let's say I was going to try to eliminate x, and I multiplied this one by 2, this one by 3. I end up with 6x minus 2y equals 10. And then 6x plus 9y equals 18. The fact that the x's matches and the y's don't means I will be able to solve this system. There will be a point of intersection, or I can take that extra step and subtract my lines, and I can see, oh, I'm actually going to get a y value. I'm not going to go solve for the point of intersection, but I can clearly see I will end up with a solution. The x's and y's are not both disappearing, like when we have 0 or an infinite number of solutions. Okay. The next one. Both of my equations are in standard form, so I'm just going to see if I can match the equations. I'm going to multiply the first line by -3. And I get -9x, so the x's are matching, -12y, those are matching, and -36. They end up being the exact same line, so I have an infinite number of solutions. The next one, I will try the same strategy. So I'm going to multiply this by 2. 2x, the x's match, -8y, the y's match. This is already telling me my two lines have the same slope. And then -6 times 2 is -12. The constants don't match. This is telling me if I were to take that elimination step, so I'm just going to cross this one out, and I subtract my lines, the x's and y's will cancel, but 12 subtract -12 is 24. That's false. I have 0 solutions. And the final one, it looks like I don't have a connection between the x's and y's, but let's just give it a try. I'll multiply the first line by 6 and the second one by 5. And we're going to end up with 30x plus 90y equals -30. And then 30x. Oh, actually the x's and y's do match. And -30. Oh, look at that. It's going to be infinite. Infinite solutions. They're the exact same line. All right. Now let's start thinking a little bit beyond grade 10. In grade 10, we always looked at 2 lines. But what about if we had 3 lines? How can they intersect? So let's draw some potential arrangements. Well, one of the ways is that there is a single point of intersection between these lines. There it is. Another one, 0 solutions, because they're parallel and distinct. I should be putting arrows at the ends of my lines. I'm just not. What about if we have 2 lines that are on top of each other and the third one is parallel? Or I have 2 lines that are on top of each other and one intersects. Or what if I have all 3 on top of each other? So we have 5 arrangements so far. What about if I have 2 that are parallel, but the third one is not? Or what if each line intersects with the other, but at different points? So those are our 7 different arrangements. I'm adding in the arrows now. So that's just a little bit to get us thinking outside the box. Now, something that we're going to see a lot in this unit is 3 variables, because when we are in 3D, we tend to have 3 different components, x, y, and z. So a little extension piece here that we will need is solving a linear system when there are 3 variables. Now, we can only do that if we're given 3 equations. 3 variables, we need 3 equations. So you can do this with substitution or elimination, totally your decision. I'm going to show this with elimination because that's my personal preference. But what I will be doing, I'm going to try to eliminate a variable. I'm going to choose x twice. So I'm going to pick 2 lines at a time, and I'm going to eliminate x. So I'm going to say this is line 1, line 2, line 3. I think a pairing of 1 and 3 would be nice. Like if I do the first equation minus the third equation. So let me just set them up. All right, the x's already match, so I'm going to subtract. The x's are gone. 2 minus 3, negative 1y, 3 minus negative 1, positive 4z, 6 minus negative 8, 14. Now, I'm going to keep this equation to the side because right now there's nothing really else that I could do. I mean, I could isolate for y if substitution was my chosen method, but I'm just going to keep it in this format. Now I'm going to pick a different pair of lines, so either 1 and 2 or 2 and 3, and I'm going to eliminate the exact same variable. I'm going to eliminate x again. That way I'm going to end up with two equations and they're both going to be about y and z, and then it'll feel very grade 10. So I think I'm going to double equation 1 and then subtract it from equation 2. So I'm going to have 2x, 4y, 6z, and 12. The second one I'm just going to copy paste. And now subtract. X's are gone. 4 minus negative 1 is 5y. 6 minus 2 is 4z. And 12 minus 10 is 2. Now I have a second equation about y and z. Now I can do another substitution or elimination on these two new equations. And I noticed that my z's are already matching, so I'm just going to place that second one right underneath, and I'm going to subtract. Negative 1 minus 5, I have negative 6y's. The z's bye-bye. And 14 minus 2 is 12. We can divide both sides by negative 6, and I just got the y value, which is negative 2. Now I can take this and plug it into either one of my previous equations. I'm just going to go in here. 5 times negative 2 plus 4z equals 2. Just going to clean this up and isolate for z. So 2 plus 10 is 12, and divide by 4, and we end up with 3. Now I still need x. I'm going to go back into one of my original equations. I think I'm just going to go into the first one. So x plus 2, but y is negative 2, plus 3, and then z is 3, equals 6. X minus 4 plus 9 equals 6. Negative 4 plus 9 is 5. Bring the 5 over, it becomes minus 5. So we end up with positive 1. And now if I was unsure of my work, I would do a left side, right side check. I know this is going to work for the first equation because that's where I got this final x value, but I can do a check in the second and third to double check. So I'm going to do it in my calculator. All right, 2x, so 2 times 1, minus y, so minus negative 2, plus 2z, so plus 2 times 3, and I got 10. Beautiful. Second equation works. Third one, x, so 1, plus 3y, so plus 3 times negative 2, minus z, so minus 3. I got negative 8. Wonderful. I'm happy with this. And I'll just write my therefore POY is 1, negative 2, and 3. So this is clearly something that's happening in 3D. We don't know what those equations represent just yet, but we will later on in the unit. So now we're going to take a little bit of a step away from systems, and we're going to get a little sneak peek of what our equations will look like for lines in this unit, because we're not just going to see y equals mx plus b or standard form in R2. There's going to be other forms called vector equations and parametric equations, and then we're even going to go into lines in R3, so, and planes in R3. So for now, we're going to get a little bit of a sneak peek. So we're used to defining lines in y equals mx plus b or standard form. But this time we're going to define our lines using a parameter. We usually use t, but it could really be any letter. Just not x and y, because x and y are the coordinates. So what these parameters and these equations are going to do, we're going to have two separate equations, one for x and one for y. So this line is defined by x is equal to 2t and y is equal to 1 plus t, where t is an element of all real numbers. Now, to create a coordinate, we have to pick a t value and sub that t value into both of these equations, x and y, and it will spit out that coordinate. So in my table here, I've already picked some t values, -1, 0, 1, 2. So let's find some coordinates on this line. So for x, we're going to do 2 times -1, 2 times 0, 2 times 1, and 2 times 2. For y, we're going to do 1 plus the t value, just like what these equations are telling us. So 1 plus -1 is 0. 1 plus 0 is 1. 1 plus 1 is 2. 1 plus 2 is 3. And now we have coordinates, -2, 0. I'm going to plot it. 0, 1. Plot it. 2, 2. 4, 3. And if I wanted more, I could pick other parameters. So, maybe I pick another one. Maybe I'll pick -3. 2 times -3 is -6. 1 plus -3 is -2. Here's another point. And it seems to be lining up nicely. Maybe I pick 5 as a parameter. 2 times 5 is 10. 1 plus 5 is 6. There we are. And now, should use a ruler, but there's our line. So it's a different way to find points on a line. You have an equation for each of your coordinates. And these are called parametric equations because the coordinates are defined by this parameter. Let's graph a new line. Let's graph line 2 on the same grid. So x is defined by t minus 2, y is defined by -t minus 3. I'm just going to show a little bit of work on the side here. I'll create a new table of values. I'm going to do it in red. So my parameter, the x coordinate, and the y coordinate. I'm just going to pick a few. I don't need, that many coordinates. So -1, 0, and 1. So x is t minus 2. So -1 minus 2, 0 minus 2, 1 minus 2. Y is defined as -t minus 3. So -1 is 1 minus 3 is -2. -0 minus 3, -1 minus 3. Here we are. I'm going to plot these points. We have -3, -2, -2, -3, -1, -4. I feel like if I just go backwards, I'll have a point of intersection. So maybe the point here. So let me just put a -2 in there just to double check. -2 minus 2 is -4. And -2, so +2 minus 3 is -1. And there we are. I just wanted that point of intersection. So there's line 2, there's line 1. Where does line 1 from part A intersect line 2? At -4, -1. Now, if those equations had been in y equals mx plus b form or in standard form, I would have done a nice substitution elimination and I would have solved specifically for x and y. But with these parametric equations, we could solve for that point of intersection slightly differently. It's still going to involve a substitution or elimination idea, but instead of solving directly for x or y, we're going to be solving for the parameter. So let's take a look at what that will look like. Now, looking back at this question, it actually wasn't the greatest idea to use the same parameter for the second line. So I'm actually just going to go in here and modify. Instead of t, I'll use a different variable. I'm going to use s. So I'm going to define line 2 as a different parameter, s minus 2, and negative s minus 3. Because lines, when I have different lines, they should actually have a different variable for the parameter. All right, with that in mind, we are trying to find the point of intersection between these two lines, and we're given an equation for x and an equation for y. Now, both of my starting equations are about x in each of the lines, so why don't I set the x's equal to each other? In the first line, x is equal to 2t. In the second line, x is equal to s minus 2. Just going to make a little note. Then I can do the same thing for the y's. I'll create an equation out of setting the y's equal to each other because I am trying to find when are the y's equal to each other, when are the x's equal to each other. So I'm going to have 1 plus t equals negative s minus 3. And now here's what I have, two equations with two unknowns. So I'm going to solve this one. You know what? Let's do substitution this time. Let's change it up. So I'm going to isolate for s. And now I'll take what s is equal to and sub it into the second equation. Being careful with my brackets. I'll distribute the negative 1 in. And now I'm just going to bring the t's to one side, constants to the other. So I'll have 3 t's on the left and negative 6 on the right. Divide out the 3. And I get t equals negative 2. So if I sub in negative 2 into the first line, I should get my point of intersection. I'm going to see what s is equal to for the second line. And then I'm just going to double check in both lines just to be safe, especially since this is our first time using these parametric equations. So I'm going to go in here. 2 times negative 2 plus 2. They actually end up matching. Okay, so let's see what the coordinate for line 1 would be. So line 1 is defined for x as 2 times t, so negative 4, which is what we are expecting, and y is defined as 1 plus t, which is negative 1, which is exactly what we saw. And I can do my check on line 2 as well. X was defined as s minus 2, negative 2 minus 2, negative 4, fantastic. Y was negative s, so negative negative is positive 2, minus 3, negative 1. Fantastic. So there's that same substitution or elimination, but the start, instead of, having our standard form equations, we had these parametric equations, and then we set them equal to each other to solve for the parameters. And there's our little twist and a little sneak peek into what we will be seeing, a very, let's say, tame or basic version of what we will be seeing, but a sneak peek nonetheless.